Okay, so today we'll be talking about some basic building blocks of operational transconductance amplifiers, or OTAs. So we'll be talking about a current control resistor, an integrator, and then finally we'll bring a second order low pass filter. We will also talk a little bit about the non-idealities of OTAs, so that when you start building your project with them, you make sure that you account for those, since they can be a lot of trouble. If you just consider the OTA to be something ideal, you're gonna have to take some time to understand what you need to do to make those components work. Okay, so let's remember the ideal conditions of the OTA. So just like we said in the previous video, ideal conditions, where we have an input impedance that it's infinity and output impedance which is infinity. The equation for it is going to be output current is proportional to GM times BD. Same thing as just saying GM times B plus minus V minus. And then GM, it's equal to IABC times K, where K is just a PVT, or process voltage, and temperature constant. Okay, so let's start talking about the basic building blocks. So we'll start with the current control resistor. Correct. So current control resistor, and we're going to start by drawing the schematic. So this is what it looks like. Here's the OTA. That's negative. This is positive pin. And to the ground. And then we got this is a grounded resistor. Okay, so we'll do a DC analysis to see how it works. So case 1 is going to be a DC analysis. We'll put IABC equal to 0. So the bias current in this case is going to be equal to 0. And so now what you do is that you apply a voltage at V minus, and you apply a step. So it's going to be apply U of t. So what you got is, once you do that, you're going to have that BD goes negative, recall that BD is just going to be equal to B positive minus V negative, or is equal also to B positive minus V negative. So it goes negative. Second, what you're going to have is that IABC is 0, because we said it before. Therefore, GM is 0, and thus I naught is equal to 0. So we are applying a voltage, but we are seeing very little current at the output. So what that means is that in theory the circuit looks like an open. It's infinity or an open. Okay, so now let's redraw the circuit. Alright, so now we'll be talking about case 2. We're still doing DC analysis. Now we are doing the second case. So, still DC analysis. And then, but now, it's going to have IABC, or the bias current, going to infinity. So, that will create, so, and now you apply a voltage at V minus, just like we did before, and it's going to be still a step. And so now what is going to happen? Well, again the same thing, BD goes negative. Now I naught is negative and flowing into the OTA, because I naught is equal to GM times VD. And now IABC is infinity. It's infinity, therefore GM is infinity because it's proportional to IABC, transconductance, and the circuit looks like a short. So by some just DC analysis, we realize that Rin is proportional to BD over IABC. Correct? If IABC goes up, Rin goes to 0. IABC goes down, Rin approaches infinity. So that was the current control resistor. Now let's talk about the integrator. Okay, so the integrator. So now let's draw the schematic. You can note some of the similarities with the current control resistor, like the feedback, negative feedback. Okay, so let's start with AC analysis. And so it's going to be assuming a constant bias current. And you're sweeping the frequency up and down, see how the circuit performs. So first, as omega goes to infinity, the OTA can charge the capacitor fast enough, and therefore we have a short. short to the output from V out. So this is V out to ground. Well, let's call it just out since it's market. Okay. And in this case, you're gonna have just that V out is equal to 0 volts. Okay, so now the second case will be when the frequency goes down. So as omega goes to 0, the OTA now has enough time to charge and discharge the capacitor, and therefore, or thus, we have that are following the input. So in this case, what is the role of IABC? So let's write that. So IABC controls the speed at which the OTA can charge the capacitor. And that is since I out is proportional to IABC by the formulas provided before. Okay, so what will the body plot look like? Well, you're gonna have this passband, and then you're gonna have it's gonna be attenuated as you increase the frequency, and then this point right here, the location of the pole, is just going to be controlled by IABC. So omega C Okay, so now we're going to take the same circuit, but then assume a constant frequency input, and then we're going to start modulating the bias current to see how the circuit performs. So the first case, this is going to be a very similar process than we did with the current control resistor. So I'm just going to write it. When IABC is very small, that means that GM is very small. And since I naught is proportional, or I out is proportional to GM, then I know this is small too. This means just like we said before, will take the cap a long time to charge. Now, here's the interesting part. Now, if BD is changing fast, and I naught is small, because IABC is small, or IABAS is small, then I out will not be able to charge and discharge the capacitor fast enough, and we will have a short at the output. Now let's look at case 2. Case 2 is when IABC or I bias is very large, or is large. So if IABC is very large, then GM is large, and I output is large. This means that now the OTA can charge and discharge the capacitor a lot faster, since it can source and sink more current. Now, what that means for us is that even if BD is changing fast, I output is large, because as we said before, IABC is large and those two are proportional. Therefore, here's the interesting part, the OTA will be able to charge and discharge the capacitor fully and keep track with the input. That's the crucial point right there. That means that we are in the passband still. Therefore, V0 equal to Vin. So this means, so after we did all that in thought experiments, what do we conclude now? We conclude that this means that by changing IABC or the bias current, we can change the cutoff frequency of the low pass filter. Since this is a single pole system, then you can move farther away from the j omega axis, correct? And that will increase the frequency at which attenuation starts to occur, or just simply the cutoff frequency. Okay, so now let's draw what happens in the body plot. So for 3 different cases, IABC is equal, so we start with 1 milliamp. Now we put in red, IABC is equal to 0.5 milliamps. and in blue we put IABC is equal to 1.5 milliamps. Okay, so let's draw some low-pass curves. So what you're gonna have a low-pass curve that looks like this, and the cutoff here is gonna be FC, and that's at 1 milliamp for IABC. Now let's draw the red curve. So it's at 0.5 milliamps, and we're going to be moving that pole closer to the j omega axis, which means that the cutoff frequency is decreasing, right? But now the passband is going to be same up until it reaches a point, and then the new cutoff frequency will be right here, and that's at 0.5 milliamps. Now the next one, since now we increase the bias current, and that pole is going to move farther from the j omega axis, which means that the cutoff frequency is going to be farther in frequency. So that's blue, okay, and it's going to be right here. So you can see this is very nice because you have a tunable low pass filter, which is what is needed in a lot of applications. So this is first order low pass filter building block. And with that you can synthesize higher order filter. We're going to talk about a second order low pass filter block. It's also called a cascaded integrator. So let's write that. Cascaded integrator. So let's write the schematic for it. So positive, and that's the input. Now you're gonna have. Okay, so that's the final schematic, and then let's talk about really quick about the intuition. Very similar to the previous example. Okay, so this is a 2-pole cascaded integrator. Of the type seen previously. Adjustable poles. So the beauty about this is that you can adjust the poles just by changing a common IABC, correct? Actually, it's going to be down here. But then keeping the quality factor of the filter constant. So that's very important. Okay, so for this filter, stages can be cascaded since the input impedance of the second OTA is ideally infinite. Further, the output of the whole filter is fed back to the input to provide negative feedback that will keep VD, the differential voltage, within reasonable limits, and provide stability. Much like using the simple integrator that we talked about before. Another important thing to note is that with this configuration, C2, C1, and IABC provide full control over the cutoff frequency and the quality factor. So the formulas for the ideal circuit, I'll talk about why they change once you start to use just off the bench OTS. So the cutoff frequency is controlled by IABC times K over 2 pi square root of C1 C2 that's equal to GM over 2 pi square root of C1 C2, and Q is equal to square root of C2 over C1 . Okay, so here we provide you with first order low pass filter building block and a second order low pass filter building block. But now we have to talk about the non-idealities of the implementation of these schematics, of these circuits. So let's talk about that. Okay, so the first, and is the most important, the one that takes you a long time to figure out why it doesn't work, VD has to, the referential voltage has to remain very small. And when I say very small, I say preferably less than 20 millivolts. And 20 millivolts. The next one, which is also very important, is the IABC, or the bias current, has a range, has to remain within a range from 0 to 2 milliamps, where 2 milliamps is maximum, this is rated max. So what I always do is that I do from 0 to 1.5. So what could be a possible implementation of our previous second order low pass filter that meets these limitations? So we'll call it possible implementation. We will do two things. We will add voltage dividers at input and on the feedback network, and add a control voltage scheme. And this will be the modified circuit with the input voltage dividers, the input to second stage voltage divider, and we got the feedback voltage divider. And for the control scheme, all what you need is really a control voltage and a biasing resistor that controls the current that is common to both OTA1 and OTA2. How would you, a simple way to do that control, to simulate a control voltage will just be a potentiometer with one wiper to VCC and the other wiper to VEE, and the middle wiper just going up to as B control. Okay, so I hope this video helps you with your next OTA implementation, let it be filters or anything else.